Alrighty, section 3.3, graph sketching, and specifically we're going to be looking at asymptotes and rational functions. So this is kind of putting the last two sections all together. So we've done first derivative test, we've done second derivative test. We have three things to look at here. We're going to review a little bit at first, limits involving infinity. Infinity. And then we're going to look at determining asymptotes. Asymptotes. And then finally we're going to look at the graphing checklist. And using that to graph functions. So let's start with a little bit of review here, reviewing the definition of rational functions. Remember, rational function, f, is a function that can be described as f of x equals p of x over q of x. And p of x and q of x are both polynomials. Q of x can't be 0, and the domain of f consists of all inputs where q of x does not equal 0. So we're going to be focusing primarily on rationals here, but all of this still applies for polynomials, just like q of x equal 1 in that case. It's actually easier, as most things are with polynomials. So let's talk about our vertical asymptotes. So what we have here is this rational function, and I've gone ahead and made the graph already in my computer to put on here. And by I made it, I mean I stole it from the book. How sneaky of me. So when we're talking about horizontal asymptotes, we're looking at the leading coefficient and the leading coefficients of the highest power term. So these tell us all of our horizontal asymptotes. And since this is x squared over x squared, this is essentially 1. And so that's why our horizontal asymptote is y equals 1 going across. For our vertical asymptotes, we're looking at the denominator, and we're setting each of these equal to 0. And so since there are two factors in this quadratic, we have two vertical asymptotes, x equals -3 and x equals 2. So this is the basic premise of how we get our asymptotes. And this will be one of the first things you do when we get to that graphing checklist. But that is what we look at. So just to kind of put this into complete form, so there's no guesswork, the line x equals a is a vertical asymptote if any of the following limit statements are true. So if the limit as x approaches a of f of x equals infinity, it will be a vertical asymptote. If the limit as x approaches a of f of x equals -infinity. So if either of these two things are true, we have a vertical asymptote. So you can see in this first diagram in part A here, we are going up towards infinity, which is our first case. We have vertical asymptote. Going down towards infinity, vertical asymptote. Up towards infinity from the right side, vertical asymptote. And down to -infinity on the right side, vertical asymptote. So we just have to check these two things. So these are our infinite valued limits, right, when our limits could actually equal infinity. So let's look at a rational function with no vertical asymptotes. So we've seen something like this before. So x squared minus 9 over x minus 3. Now this has no vertical asymptotes because we can factor x plus 3x minus 3 over x minus 3, cancel, and remember when we were doing limits, I said very vehemently that f of x does not equal x plus 3. What we're saying is the limit as x approaches 3 of f of x exists, but f of 3 is undefined. And remember, we called this, when you can factor it out in the limits here, we called this a removable discontinuity. So when you can factor this, this is a removable discontinuity. Discontinuity, which was a hole in the graph itself. So our function is still the rational, this thing over here. It acts like x plus 3 everywhere except at 3. And at 3, it has a hole, or a removable discontinuity. So let's take a look at this next example, determining vertical asymptotes. So we can't do any cancellations. So there's no cancellations. Cancellations. So we just set the denominator equal to 0. Denominator equal to 0. X times x minus 5 times x plus 3 equals 0. And we get x equals 0, x equals 5, and x equals negative 3. All of these are vertical asymptotes. So this is the shortcut way to find vertical asymptotes. If we go back to this definition with the limits, as we approach, let's say 0, the limit as x goes to 0. Let's do this off to the side here. So the limit as x goes to 0 of 3x minus 2 over x times x minus 5 times x plus 3. Well, this becomes negative 2 on top. We're going to hold off on writing what x becomes. This goes to negative 5. This goes to positive 3. And now we'll put the 0 in. So essentially what we have is negative 2 over 0. And even though we don't write this as a term, as a number, we say that this approximately goes to negative infinity, because we have negative, and when we divide by 0, we say it's essentially infinite. So negative infinity satisfies our second limit up there in that definition, which means that we have vertical asymptote. And you can show the same thing. This one goes to positive infinity, and this one goes to negative infinity as well. But this is the shortcut. This is the way that we're going to do it, is setting that denominator equal to 0. So, flip the page here. The practice here for you to find vertical asymptotes. And I want you to try and factor first. And yeah, let's say pause the video here and actually try this. And I'm just going to tell you the answers in a second. Okay, 1 second's up. So x equals 0 is a whole, because it can be canceled. And x equals 1 and x equals negative 1 are the vertical asymptotes. So if you're not sure how I'm doing this, go back to the last page, follow the same steps, try and simplify and cancel anything that you cancel as a whole, and then set your denominator equal to 0. When you do that, those give you your vertical asymptotes. So our shortcut here is just reiterating what I've said, so you have it and you can go look at it. So given a rational function p of x divided by q of x, the line x equals a is a vertical asymptote whenever q of a equals 0. So that's just saying exactly what we've been doing. Set your denominator equal to 0, figure out what values that denominator is 0 for. So vertical asymptotes are the easy ones. Horizontal asymptotes are the less easy ones. So the line y equals b, oh excuse me for yawning, is a horizontal asymptote if either or both of the following limits are true. So the limit as x approaches negative infinity of f of x equals b, or the limit as x approaches positive infinity of f of x equals b. So the graph of a rational, it may or may not cross a horizontal asymptote, and the reason for that is our horizontal asymptotes are defined by the end behavior. It's the infinite and negative infinite side, so the tails. So in between, close to the axis, in the middle, you can still cross horizontal asymptotes, which is different from vertical asymptotes. You never cross a vertical asymptote. Horizontals can be crossed close to the axes, not at the tails. And horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. The degree of the polynomial, remember, is one variable is the highest power in that variable. Now, this does mean something very specific. There's only two limits that we can check, which means that there is a maximum of 2 horizontal asymptotes. That's it. You can have 2, you can have 1, or you can have none. So I've got some examples here, graph examples. So here we have the limit as x approaches infinity, f of x goes to b, and so it's coming up towards b, and it's going to level off here, which makes that horizontal asymptote. Here we have f of x approaching negative infinity, and it's going to level off towards b as it gets close to negative infinity. And then here's an example of when we can cross. So close to the axes, we can cross it. We cross it twice, but as we get further out towards the tail, it's going to level off and stop. And out here, it's not going to be able to cross this asymptote anymore. And that's what we're talking about. When you're close to these axes, you can cross horizontal asymptotes. But the further you get out, it means you can no longer cross them, because you're tracking end behavior with these two limits. And this is just saying the same thing as said there. Horizontal asymptotes are found by determining the limit of the rational function. So let's find some horizontal asymptotes. So the first thing we do, we check two limits as x goes to negative infinity and as x goes to infinity. And this is of 3x minus 4 over x, 3x minus 4 over x. So, as we go towards negative infinity, we know the negative 4 really doesn't matter anymore, because negative 4 compared to negative infinity is nothing. So we can approximate this with the limit as x goes to negative infinity of 3x over x. And we know that this is just going to equal 3. And so y equals 3 is a horizontal asymptote. And then same thing down here. As we go towards infinity, that negative 4 doesn't matter. So this gets approximated the same way. Oh, this is positive infinity now. 3x over x, and this again is just going to equal 3. And in both cases, that's because this x can be canceled. So, once again, y equals 3 is a horizontal asymptote. So this is the case where we can have one horizontal asymptote, where our two limits equal the same value. And so this is our only one. So we flip the page. We have another little example. So the next thing is, when you're doing horizontal asymptotes, it's always these two limits as we go to negative infinity and infinity. And this is of 3x squared plus 2x minus 4 over 2x squared minus x plus 1. And same thing down here, plus 2x plus minus 4, 2x squared minus x. X got a little squash there, plus 1. And as we go towards negative infinity, because we have squared x's, the linear terms and the constant terms, these four terms don't matter. And we can approximate this as the limit as x goes to negative infinity, 3x squared over 2x squared. And the same thing down here, limit as x goes to negative infinity, 3x squared over 2x squared. And both cases, this is going to equal 3/2, because our x squared terms will cancel. So y equals 3/2 is a horizontal asymptote. Now, not every single rational function is going to only have one horizontal asymptote. Sometimes they'll have two. So, a little practice problem here. Try this out, pause the video, do the same thing. It's your two limits every time, the same ones. Negative infinity and infinity. So I'm going to work these out now. Hopefully you paused it and you tried it. So this is the limit as x goes to infinity of 2x plus 3 over x cubed minus 2x plus 4. And this can be approximated by the limit as x goes to infinity of 2x over x cubed, which is the same as the limit as x goes to infinity of 2 over x squared. And as x goes to infinity, the denominator here is going to go to infinity, and so the whole fraction is going to go to 0. So that means that y equals 0 is a horizontal asymptote. And then down here, 2x plus 3 over x cubed minus 2x plus 4. Again, since we're going to negative infinity, we can approximate this. So the limit as x goes to negative infinity of 2x over x cubed, which is nothing more than the limit as x goes to negative infinity, 2 over x squared. And this is going to also equal 0. So this is our only horizontal asymptote. So one thing that we need to discuss is when the other situations happen. So all of our examples have been one horizontal asymptote, and that's because most rational functions only have one. But there are times that there are two, and so we can find the horizontal asymptote. We have some shortcuts here. So if the degree of the numerator is greater then the degree of the denominator there are no horizontal asymptotes. So no horizontal asymptotes exist. And that's because the numerator, as we go towards the tails, overtakes the denominator because it has a higher power. Remember, its degree is the highest power that you see, and so that overtakes it. The flip side, if the degree of the numerator is less than the degree of the denominator, then the only horizontal asymptote is y equals 0. And that's the example that we have right here above us. Our degree of our denominator is bigger, so the degree of the numerator is less, and we got y equals 0. And the last is if the degrees of the numerator and denominator are the same. Denominator and numerator are equal, then the horizontal asymptote will be the ratio of the leading coefficients. And that's what we saw here. So the two degrees were the same, squared and squared. And so our horizontal asymptote ended up being the leading coefficients, one over the other. Excuse me. So there is one other type of asymptote, and this is the linear asymptote. It's neither vertical nor horizontal because it's a line. And it's called either a slant, oblique, or oblique asymptote. I will typically call it slant asymptote. Just know that the book will also call it oblique from time to time. So for any rational function of the form p of x over q of x, a slant asymptote occurs when the degree of p of x is exactly 1 more than the degree of q of x. So when you are 1 degree higher. And the graph of a rational function can cross a slant asymptote anywhere. They're used by finding division, either polynomial long division or synthetic division. Long division or synthetic division. So let's go ahead and take a look at a couple examples using that. I also have a graph of something with an oblique asymptote or a slant asymptote. So you can see we have this slant asymptote. It's not a horizontal one, it's a slant, and these things are going to curve. And they follow this asymptote instead. Now, to find that, that's what we're doing in this first example. We're going to divide. So we'll do long division, so x minus 1 into x squared minus 4. I know it's probably been a while since we've done polynomial long division, so we'll walk through this step by step. So you're always looking at the first term to the term that you're on. So how many times does x go into x squared? That's x times. And then x times x gives you x squared. X times -1 gives you negative x. And then you subtract, just like you would regular division. So x squared minus x squared is nothing. We have no x's here, so we end up with an extra x, and then the -4 has nowhere to go. And then you ask how many times can x go into x minus, or how many times can x go into x? And that's exactly 1 time. 1 times x is x, 1 times -1 is -1, and then we minus that. X minus x, 0. -4 minus a -1 is -3. And so we end up with x squared, ignore that, -4 over x minus 1 is equal to x plus 1 plus -3 over our original divisor, x minus 1. No. Yeah. No, it should be x squared minus 4. I'm a crazy person. But this is the rational piece. This is the linear piece. And this tells us our slant asymptote. So this is how we got this. You know what? I don't know why I did that. I was right the first time. It's over x minus 1 here. Sorry about that. But this isn't the important part. It's this, because this is what we're trying to find. So you do your long division, and then what you get here, once you hit your remainder and you can't go any further, because x can't go into -3, that piece is your slant asymptote, which is the asymptote that we had right here. So I want you to try this long division. I'll help you set it up here. So you're dividing x squared minus 3x plus 2 into x cubed minus x squared minus 6x. So that's what you need to divide. So pause the video, try this out. And remember, when you get to a point where x squared can no longer go into something, you should have a linear term up here, and that will be your slant asymptote. So pause it and try. Okay, so I'm going to walk through it now. X squared goes into x cubed, x times x squared is x cubed, x times -3x is -3x squared, x times 2 is positive 2x, and then we're going to minus x cubed minus x cubed is 0. Negative x squared minus a -3x squared is the same as positive 2x squared. Negative 6x minus 2x is negative 8x. So now x squared goes into 2x squared 2 times. We get 2x squared. We get negative 6x. We get positive 4. And then you're minusing that. 2x squared minus 2x squared, nothing. Negative 8x minus a negative 6x is negative 2x. 0 minus 4 is minus 4. And now x squared cannot go into negative 2x. So this, y equals x plus 2, is the slant asymptote. And that's how you do it. And this is only when you have your degree on the top is 1 more than the degree on the bottom. If it's x to the 4th and x squared, you wouldn't do this because you wouldn't get a linear term. Okay. So moving on now, we are into the graphing checklist. So these are the 7 things that we have to do to get a calculus quality graph. Quality graph. So the first is your intercepts. You need to make sure you have your intercepts, that's the x and the y. The second thing is your asymptotes. All 3 types you have to check for: vertical, horizontal, or slant. A lot of times I tell my students, remember your VHSs, because it's fun to have little acronyms. After you have your asymptotes, it's time to take your derivatives. So we need f prime of x and f double prime of x. Once you have your derivatives, we need to find our critical values. And with the critical values, we need the intervals of increasing and decreasing. And remember, your critical values come from where your derivative is 0, your first derivative. After you have your critical values, it's time to get your points of inflection, POIs. And with those, we need our intervals of concavity. And remember, you find your points of inflection by setting your second derivative equal to 0, or where it's undefined. And number 6 is finally to plot all of these points. So that's your intercepts, your extrema, your points of inflection, everything. Because as you work through this list, you'll be getting a bunch of points. Once you have all those, you can sketch the graph. So once you've plotted your points, depending on whether you did the first derivative test or the second derivative test to identify your extrema, you'll know the shape and you'll know the direction. And then you can sketch. So this is a lot. There's a lot happening here. So we'll go through this example together. We'll do it one at a time. And we'll just take it step by step. So it's a good idea to have the checklist in front of you as you start this. You need to know to do all of these things without it, but you can have it in front of you. So starting with 1, our intercepts. Remember, the x-intercept is the hard one. The y-intercept is where f of 0 is. So f of 0 equals 8 over 0 minus 4, which equals -2. So that's our point, 0, -2. Then our x-intercept is where 8 over x squared minus 4 equals 0. And this fraction can only equal 0 where the numerator equals 0, where 8 equals 0, but this never does. 8 does not equal 0, so that means there's no x-intercept. Right, number 2 are asymptotes. So for vertical asymptote, we're going to set the denominator, x squared minus 4 equal to 0. That's going to give us plus and minus 2. So we have two vertical asymptotes. Our horizontal asymptote, looking at 8 over x squared minus 4. The degree of our numerator is less than the degree of the denominator. So that means our horizontal asymptote is going to equal y equals 0. Now there's one thing that we can do here to verify this. If we have a different horizontal asymptote, that means that we do cross the x-axis, but we already know we don't have an x-intercept. So when you don't have an x-intercept, you are going to have a horizontal asymptote at y equals 0. Now, remember, having an asymptote does not mean you have no x-intercept. It's not a two-way street. If you have no intercept, you will have an asymptote. But if you have an asymptote, remember we can still cross horizontal asymptotes close to the axes, close to the origin here, because this is only about the end behavior. So x-intercept being nowhere, having no x-intercept implies this, but this does not imply this. Not a two-way street. And since our numerator is less, we don't have any slants, so we don't need to check. So now we go to take our derivatives. So I'm going to write f of x as 8 times x squared minus 4 to the negative 1. F prime of x then is negative 8 x squared minus 4 to the negative 2, doing the general power rule. And then the chain rule, derivative of the inner is 2x. And I'm going to rewrite this as negative 16x times x squared minus 4 to the negative 2. And then our second derivative, f double prime of x, is going to be, using the product rule, negative 16x times negative 2 times x squared minus 4 to the negative 3 times 2x. And I need a 1 parenthesis down there, and then plus negative 16 times x squared minus 4 to the negative 2. So we do need our points of inflection. And so simplifying this is negative 16x times 2 times 2. So this is not negative 16, it's going to be positive 64x squared over x squared minus 4 to the third minus 16 over x squared minus 4 squared. Now, what do I have here? Yeah, let's get another piece of paper here. Did not count on how long this one would be, for whatever reason. So now we have our derivatives. Step 4 is to find the critical numbers. So f prime of x equaling 0 or undefined. So f prime is negative 16x over x squared minus 4. And so when we set this equal to 0, this is only going to be true when negative 16x equals 0, which is only true at x equals 0. And then we are undefined at x equals plus or minus 2, because that's where our denominator is undefined. So these are our critical numbers. So here's where you have your choice of going first derivative test or second derivative test. So we're going to pause on testing these critical numbers and go figure out where our second derivative equals 0. So this is 64x squared, and then I'm just going to multiply by an extra copy here, minus 16 times x squared minus 4, all over x squared minus 4 cubed. So I'll bring that back in a bit. And we need this to equal 0. Again, this is only going to happen when 64x squared minus 16x squared plus 64 equals 0, which is, did I multiply that right? 16 times 4? Yeah. So this is going to be at 48 x squared plus 64 equals 0. And can this ever actually equal 0? That's the question that you have to ask. Well, since this is getting squared, this will be positive. We'll be adding a positive, and the answer is going to be no. And if you're not sure, you can always continue solving, and then when you go to take the square root, this is imaginary. So there's no places where f double prime of x equals 0. But there could be still undefined stuff, and there is 2. So we're undefined at x equals plus or minus 2 again. So we have some choices. So now we can come back and we can look at our critical numbers versus our potential points of inflection. Now, when you're trying to make your decision, if you have points of inflection that are also critical numbers, remember our second derivative test is going to be inconclusive because they match. That means that this tells us we're going to have to do a first derivative test. So I'm going to classify at -2, 0, and 2. And so this is our first derivative test. So I'm going to pick f prime of -3. I'm going to pick f prime of -1, f prime of 1, and f prime of 3. Now remember, we don't need to know these numbers, we just need to know the sign. So coming up, let's rewrite this so I don't have to keep sliding. 16x over x squared minus 4. So when we plug in -3, negative times negative makes this positive on top. So we're going to have a positive, and then 9 minus 4 is 5, so this is positive. So this will be greater than 0. So that means we are increasing. When we plug in -1, negative makes this positive. And then 1 minus 4 is -3, so this is less than 0. So this is going to be decreasing. I think. No, look what I did. This is supposed to be squared. I forgot to finish it. Doesn't change our points of our critical numbers, luckily. So this will still be positive, so this will still be increasing greater than 0, increasing. We plug in 1, now we have a negative over a positive. So this will be less than 0, this one's decreasing. And then when we plug in 3, what do we have? This will be negative. This will be positive. So this is less than 0. So this is decreasing. So increasing, increasing, decreasing, decreasing. Now, because we do have these points of inflection to take care of, we do need to plug these in. So I'm going to set up a test for concavity at -2 and 2. And our 48x squared plus 64 over x squared minus 4 cubed. This is our second derivative. So that just comes from our simplification here over the right denominator. So I'm going to test f double prime of -3, f double prime of 0, and f double prime of 3. So when we plug in -3, we have positive, positive. 9 minus 4 is positive. So this whole thing is positive, so we're concave up. Then we have plugging in 0, positive, negative. 0 minus 4 is negative, so concave down. And then plugging in 3, the same thing that happened with -3. This is positive. 9 minus 4 is 5, which cubed is still positive. So we have concave up. So now we can combine this with our little checklist from the last section we did. So I have that here. So this is one of the reasons I gave you this, so don't worry, this will come back. But we have these general guidelines. Increasing concave up looks like this. Increasing concave down looks like this, and so on. So we can look at our intervals. So we have increasing to -2 concave up. So we know it's going to look like that first tick mark here. Then we have increasing concave down until 0, which means that it's going to look like this. And then after 0, we have decreasing concave down. So that means it's going to look like this and create from here at 0 down to here. And then we have decreasing and concave up. So that's going to look like this. So if we go back to our graph here, and we start plotting our points. So we have 0, -2. We have no x-intercept. The y-intercept was 0, -2. Our critical number was 0, -2. Was that x equals 0? And if we look, our critical number increasing to decreasing should be a maximum. We have asymptotes. So our horizontal asymptote is at y equals 0. Our vertical asymptotes are at 2 and -2. -2. So always draw your points and then your asymptotes. Now we can match up our drawings. So going back to this again, just to reiterate what I just said, we are increasing and concave up. So that means that we're going to have a shape that looks like, where'd it go? This, and that's until -2. We can't cross this. So all we usually do is just check a point. So if you plug in -3, you get 8/5, so it's going to be on the positive side, so it looks like this. we don't need to be perfectly exact. If you want to plot -5, 8 over, or -3, 8 over 5, you can, but you don't need to. Then from -2 to 0, we are increasing and concave down. So increasing and concave down. Increasing concave down looks like this, and this is until 0. So that means we look like this on that half. Then on the second half, we are decreasing and concave down. So decreasing and concave down looks like this, starting at 0 and going down. Like that. And then the last section, we are decreasing and concave up. So decreasing and concave up looks like this, starting at +2 and going towards the axis like this. And this is a pretty dang good graph of f of x. So there's a lot going on. We needed a lot of space to work this out. These are not short problems, I understand that. So this one is a little bit easier. So I recommend you try this one. Try and walk through all the steps. I'm going to sketch the graph right now so that you have it and you know what it should look like. So in this one, I will tell you, you do have a slant asymptote. The slant asymptote is x. So let's use this color. So we should have a slant asymptote for the line y equals x. You have a maximum at 1, 5. You have a minimum at -1, 2, I believe, or something like that. -1, -2 down here. You have a vertical asymptote at x equals 0. And then when you connect these, it does this, and this, and it does this, and this. Should this be? Yeah. So that's what your graph looks like. I want you to have this so you know what your end goal should look like. Do work through, oh, this should have been a something else. This should be not a 2, should be a -3, right? But work through this and see that you get this. I believe my point might be off here, but this is the general shape. Okay, so we will pause there or end there. I know it's a long one, but it's a hard section. So take your time. Make sure you get in contact with me or O'Neill for office hours. The graphing is one of the hardest things we do in the class.